Now let's try to read the question first and try to figure out what's given. Our bodies have a natural electric field that is known to help wounds heal. So we are measuring something in this problem, and that is the rate at which wounds heal. And how do we measure it? The rates at which new cells closed is how it is measured. So the question here is, what if the natural electric field in the body is changed or reduced or increased? How does that affect the ability for our bodies to help wounds heal? So a change in electrical energy, will it slow down the healing? So we have to think about how healing is measured in this problem. Healing is measured by the number of new cells that closed. So if the healing is slow, then the number of cells that closes will be less than what is in the natural healing process, is less than the number of cells closed in the natural healing process. So it's important to understand how it works. So in this case, this is how the experiment was conducted. So the newt got razor cuts on the left limb and on the right limb. In one of the limbs, it was the control limb in which the electric field was the natural electric field of our body. But in the other limb, the electric field was reduced, so that becomes the experimental limb. Now the control limb and the experimental limb come from the same newt. So the same newt gives two different numbers. So the same newt gets two different treatments, the control and the experiment. So when the same person or the same individual gets two different treatments, then we can conclude that it is matched pair. And that is an important observation to make right at the beginning of the problem, because that helps us decide which process to use. So first, we have to make it clear to ourselves that this is a matched pair problem. We know that because it's the same individual that's given two different treatments. Now, once we know that it's a matched pair problem, we know it can be reduced to a single sample problem. So it's no longer two individual samples when it's coming from the same individual. So that's what makes it a matched pair. And if it's matched pair, then we need to use the matched pair procedure. So in order to use the matched pair procedure, we need to first determine whether we want to take the difference that we need to do anyway, take the difference. But which way does the difference go? Should we go control minus experiment, or should we go experiment minus control? And it doesn't matter which way we go. We just need to make sure that we understand whether the difference is positive or negative. So let's think about these two, control minus experiment and experiment minus control. So if the reduction of electrical field in the body slows healing, then the number of cells that are closed, new cells that close in the experimental group, must be less than the number of cells that close in the control group. So in that case, C minus E is a positive number. Now, if C minus E is a positive number, then E minus C should be a negative number, because in the experimental limb, the number of new cells closed is going to be less than the number of new cells closed in the control limb, which is the body with its natural electrical field. So I would suggest taking C minus E because it's just cleaner to deal with positive differences. So now we're going to convert this matched pair problem. We're going to convert it to a single sample problem. And how do we convert it to a single sample? By taking the difference in the healing rates. So that would be D. So for example, for Newt number 8, the difference is 36 control minus experimental 33, which is a difference of positive 3. If we look at the Newt number 3, we take control first, which is 44, minus experiment, which is 47. So the difference is negative 3. So make sure you're consistent when you take the difference, take control minus experiment, and then make sure you pay attention to the signs. So for each Newt, we need to find the difference, and that is the first step to solving a matched pair experiment. So the original data, which is the experimental healing rates and the control healing rates for each Newt, so there are 14 Newts, so the sample size is 14. We decided that it is a matched pair experiment. So the first thing to do in a matched pair experiment is to take the difference between control and experiment. Here we decided to take C minus E because most of these numbers will be positive. So 25 minus 24, control minus experiment is 1. 13 minus 23 is negative 10, so control minus experiment is negative 10. So now we have a third column which contains all the differences in the control and the experimental healing rates. Once we have that last column, we can forget about the data that is given because that's no longer important. All we have to do is deal with the last column, which becomes our new variable. So our new variable is the difference, and remember that the difference was control minus experiment. So this becomes our new sample of data, and that's the reason why now the matched pair problem can be treated as a single sample problem. And the variable here is the difference. So the variable in this new column that we have constructed from based on the control and experimental data is our new variable, which is the difference in the control and experimental healing rates. So now we have to organize the presentation of our solution in the 4-step process. So the first step is to write a statement. So in this problem, we will find evidence. So we're trying to prove something here. We'll try to find evidence that changing the electrical field in newts slows healing. So what we're trying to do here is to prove something, find evidence that changing the electrical field slows the healing process in newts. So clearly at this point, we can be sure about one thing. This is not a problem where we have to construct a confidence interval because we are not estimating the mean healing rate of newts. What we're doing here is trying to find evidence that changing the electric field slows healing in newts. So finding evidence is the same as doing a hypothesis test. So that's our first step, making a statement. So we're going to find evidence to show that changing electric field in newts slows healing. The next step is to make a plan. How do we solve this problem? So we've done part of the thinking and the solving process already. So what exactly do we have to write in this portion of it? So here we start off by first saying that the problem is a matched pair problem. So first when we read the question, we recognize that it is a matched pair problem. So that's the first thing. So it's a matched pair. Now, once we determine that it's a matched pair problem, the next thing is reading the question further and noticing that what we need to do is a significance test or a hypothesis test. It is not estimating the mean where we have to find the confidence interval. So it's a matched pair problem. The next thing to know is to do that we're doing a hypothesis test. Putting the two together, we can say that we will treat this as a matched pair problem and do a hypothesis test using a T procedure. So since it is a matched pair problem, we'll use a single sample T procedure to do a hypothesis test. And the formulate portion always ends with a formula. And in this case, the formula is the formula for finding the T statistic, which will eventually help us solve the problem, which is the hypothesis test. So the formula is T equals, since it's a T procedure, it's T equals x bar minus mu naught divided by S over radical n. So in this case, sigma is obviously not given, and in place of sigma, which is the population standard deviation, we use the sample standard deviation. So S is the sample standard deviation, so standard deviation from the sample, and we know that n is the sample size, so there are 14 newts, so that's 14, the sample size is 14. Mu naught comes from the null and alternative hypothesis, which we'll soon set up, and x bar is the sample mean, so average that comes from the sample. So a formulate portion of it always ends with a formula, which will help us solve the problem. So the next part is actually solving the problem. Now, if it is a hypothesis test, the first thing to do is to set up the null and alternative hypothesis. So what we're trying to do in this problem is to find evidence that changing the electric field slows healing. If we're trying to prove that it slows healing, what we're really trying to do is prove that control is greater than experiment. Since our difference, which is equal to the new variable x, that is the single variable that we're dealing with, is control minus experiment, the mean of all the x's, we can call it mu, and what we're trying to prove is mu, the mean of all the x's. Since c is greater than e, this would have to be positive, which means mu is greater than 0. So what we're trying to prove is that mu, the mean, is positive, which is the same as saying that mu is greater than 0. So what we're trying to prove is always the alternative hypothesis. So the null hypothesis is basically what we are fighting against, what we are trying to disprove, and that is that there is no difference. So this is a no difference statement. If there were no difference, if there was absolutely no difference in the control and experimental healing rates, that is basically saying that control has to equal experiment, and that also means that control minus experiment equals 0. And if we take the average of all the zeros, obviously that would be equal to 0, and therefore the population mean equal to 0. So that is the null hypothesis, which is the no difference statement, and we'll find evidence against the null hypothesis, which states that there is no difference. And that's how we're going to prove that there is a difference, and specifically that mu is greater than 0, which means the control healing rates are greater than the experimental healing rates. So the first step is to set up the null and alternative hypothesis. The next step is to fix a significance level. For any hypothesis test, we need a standard by which we can decide whether to reject the null hypothesis or fail to reject the null hypothesis. So the question really is, how far does our sample mean fall from what is believed to be true, which is mu equals 0? If it falls far enough, then we can say that we have evidence against the null hypothesis. But how far is far enough? Alpha is the number that tells us how far is far enough from the center, which is believed to be true. So we set the significance level alpha to be equal to 0.05, and if the question doesn't say anything different, then that's exactly what we fix the rate to be, 0.05. And then of course we compare our p-value to alpha to make a conclusion. Now the next step is to do the calculations. So we're in the solve part. We already know which formula to use based on what we've written in formulate. This is the formula that we're going to use to find the T statistic. Now let's see what we have that we can use to find the T statistic. We're going to enter all the numbers in that last column, the new variable, which is the difference, into our calculators, use the statistical function to find x bar and s, which is the standard deviation, s which is the standard deviation of the sample, and x bar which is the mean of the sample. And this, use a calculator to do it. The next thing is n. N is the sample size. We have 14 newt, so that becomes the sample size. We need to figure out what mu naught is. In any formula related to hypothesis testing, mu naught always comes from the null and alternative hypothesis. So in this case, the null hypothesis is mu equal to 0, whatever this number is on the right side. And alternative, you'll see the same number, mu greater than 0. So this number 0 becomes mu naught. So we know x bar, it's the mean of the sample. We know mu naught, which comes from the null and alternative hypothesis. We know n, which is the sample size, and we know s, which is the standard deviation of the sample. So first we make a list of all the things we know, plug in the numbers, use your calculator, make sure you have parentheses around these numbers, and figure out this number. Just check my calculations, make sure it is correct. It'll be somewhere around this number, 2.02. That is called the T statistic. Now let's see where we are right now. The null hypothesis always tells us what we need to believe. We need to believe that there is no difference in the healing rates, which means mu equals 0. So 1. So the next, it tells us the T statistic, and the T statistic is 2.02. Now we need to find out if this is far enough from the center that we can claim that the center is not true. If the sample mean falls far away from the center, which we believe is true, then that tells us that something is wrong with the center, in which case we can reject the null hypothesis. Now how do we know that our x bar, and once it's standardized it becomes t, falls far enough from the center? We do this by calculating the area to the right of, in this case to the right of, since it's a one-sided test, since it's a greater than 0, it's a one-sided test. So we find the area, and that is called the p-value. Once we find the p-value, based on the significance level that we've set, we can decide whether to reject the null hypothesis or fail to reject the null hypothesis. So the first thing to do is use table C to find the p-value. Now once you have the T statistic, it tells us where the x bar that we got sits on the T distribution. In order to find the p-value, which is the area either to the right or left of the T statistic, depending on which tail we need to look at, we need to find the p-values for T. What is the p-value for T? First, in order to find the p-value for T, we need to refer to table C. But unless we know what the degrees of freedom are for this problem, it's impossible to find the p-value. So the degrees of freedom is 1 less than the sample size. So that is 14 minus 1, which is 13. So now go to the T distribution table, which is table C. Go to the row headed by 13. So it's the 13th row. Look under degrees of freedom 13. Look at the row and look for numbers, the two numbers between which T equals 2.02 lies. And when you look at the table, you'll notice that the two numbers are 1.771 and 2.160. Now go right down and find the one-sided p-values corresponding to these two T values. So when you go down the column, the one-sided p-value corresponding to 2.160 is 0.025, and the one-sided p-value corresponding to 1.771 is 0.05. So you know that the p-value corresponding to T equals 2.02 must lie between the smaller number on the left, which is 0.025, and the larger number on the right, which is 0.05. So since the p-value for T equals 2.02 lies between 2.025 and 0.05, it is quite clear that the p-value that our T statistic, which is 2.02, can assume is between 0.025 and 0.05, and no matter what it is between these two numbers, it has to be less than alpha, which is our significance level. So clearly we have evidence to reject the null hypothesis because our p-value is less than our significance level, 0.05. So now we make a conclusion. We say we have evidence, and as soon as you have used the word evidence, you need to present your evidence. Your evidence is the p-value. You don't know exactly what it is, but you know it lies between 0.025 and 0.05. So we have evidence to show that that changing the electric field in newts slows healing. So our null hypothesis was that mu is equal to 0, which means control minus experiment. The average is equal to 0. That is, there is no difference between the healing rates of control and the healing rates of experimental limbs. So that is what we reject. What we're rejecting is that there is no difference. And what that means is that we have proved that changing the electric field slows healing, which is really the alternative hypothesis. Now what if, and we are just looking at various scenarios, what if it turned out that our p-value, and this is only an what if situation, this is not true, what if our p-value was greater than 0.05? Now if this had happened, then obviously we do not have enough evidence to reject the null hypothesis. But if you do not have enough evidence to reject the null hypothesis, it does not mean that we accept the null hypothesis. The only conclusion we make is that we do not have enough evidence to reject it, but we never ever say that we accept the null hypothesis.